Hi everyone, my name is Covenant Adinuga and I'm a sophomore majoring in maths and computer science at Fisk University. Today I'm going to be talking about a particular final project I worked on which focuses on predicting and classifying the concentration of fine particulate matter in urban cities using different machine learning algorithms. So a bit background on what I worked on. I worked on a particular thing called atmospheric aerosols, which come in different shapes and sizes. And these atmospheric aerosols are one of the major air pollutants present in the world today. Fine particulate matter PM2.5, which is a type of atmospheric aerosol, is an air pollutant that is so small that it can easily infiltrate the respiratory system and reach the very depths of the lung. So because PM2.5 is very small in size, it can easily infiltrate and go through the respiratory system and cause very much harm to the lungs. So rather than PM2.5 being a single pollutant, it's a combination of many chemical substances. It's a combination of many chemical substances. It's not a single, it's a combination of so many chemical substances. And high level of this particular air pollutant is a major cause for people's health because, like I said earlier, they are so small. It's so easy for them to reach, the fragile parts of the lung and cause harm. So this PM2.5, the level at which is considered unhealthy is when a 24-hour concentration rises above 34 micrograms per meter cubes. And long exposures to this pollutant at such high levels can increase the risk of developing adverse effects from the exposure. This is the reason why being able to predict and know and foresee the particular levels of this particular pollutant can be very useful in helping us prevent people from having so long exposures to it and prevent people from being exposed to it for a long period of time. So next I'm going to talk about my data set. So my data set is divided into both the training and testing sets in form of CSV files. So the thing about my data set was that it had a particular column which was called the target column, and that target column consisted of the daily mean concentration of PM2.5. This target column was present in my training set, but it was not present in my testing sets. So the goal of my research of my software in general is to provide the target column for the testing set. So I am going to perform my training and predicting on my training set, create a model and be able to predict the target column, which is the daily mean concentration of PM2.5 in my testing set. So this data set, which was divided into two, came from three main sources. One is ground-based air quality sensors that measure the target variable, which is PM2.5, and the target column, which is the daily mean concentration, like I said earlier. There are columns for minimum and maximum readings on each day, the variance of the readings, and the total number of sensor readings used to compute the target value. This data is not only provided for the training set. This data is only provided for the training set, like I said earlier. The goal of the research is to accurately predict the target column for the testing set. The second source where my data set came from is the global forest system that records weather data like humidity, temperature, and wind speed. And lastly, the Sentinel-5P satellite that measures various pollutants in the atmosphere. All data for each pollutant is obtained from the offline level 3 dataset available in Google Earth Engine. For a given pollutant, for example, nitrogen oxide, all the data from the Sentinel-5P dataset is provided. This includes key measurements like NO2 column number density, as well as metadata like the satellite altitude. So next, I'm just going to a key problem that a particular issue I had with my data set while I was working with it was that they are not 100% complete. You see, some columns are missing, some values are missing, some rows are missing values, some columns are missing values, and some locations have no sensor readings for a particular day. So those rows were excluded. There were also gaps in the input data, particularly in the satellite data for CH4. Now, the machine learning methods and tools I used to carry out my project, it was both divided into classification and regression tasks. So what I wanted to do was I didn't only want to predict the values for testing data, daily mean concentration for my testing data. I also wanted to classify that testing data into high and low. I wanted to be able to say, okay, this is too high on these days, or this is too high on those days. So I had to determine what model I will be best for me to use for classification and also regression. So I tried about 4 different models for each task. And for the regression task, I use linear regression, KN neighbors regressor, decision tree regressor, and random forest regressor. And for the classification task, I used logistic regression, KN neighbors classifier, decision tree classifier, and random forest classifier to try to predict and classify my already predicted values. The tools that we are using in the pre-processing data training and training and testing models includes Python programming language, NumPy and pandas for data pre-processing, scikit-learn for machine learning models, and result analysis. So these are the results after I fitted my trained my data, I predicted my data. I was able to discover or to determine what model will be the best to use to predict my data, and this was how I was able to do it. So the data was split into training and testing data sets, right? 5-fold cross validation was used to search the best models for prediction. Here are the results when the models were evaluated using the training and testing split. So the thing is that I wanted to try 2 different methods to test my models, right? And the first method I could think of trying was the ordinary train test split. I also wanted to use k-fold cross validation and divide my data into 5 folds. So when I used my train test splits, if you noticed, the values on the left are the root mean squared error, and the values on the right are the r squared values. And if you notice, you see that obviously the highest there is KN neighbors regressors. For the root mean squared error, it has a value of 36.64, and the lowest is random forest regressor, which has a value of 13.7. And we know that as it gets closer to 0, I'm talking about the root mean squared error, as it gets closer to 0, it's the model is better as it gets closer to 0 for the root mean squared error. So as we can see from there, we can tell that since random forest regressor with a value of 13.72 is the closest to 0, it is the best model to use in terms of the root mean squared error. Now we come to the r squared error, where we can see that the values are approaching 1. Again, this time KN neighbor regressor, which k neighbor regressor is the one that has 0.35, which is actually the lowest, as opposed to it being the highest when we are looking at the root mean squared error. We're looking at the r squared, is actually the lowest with a value of 0.359. And here we have our random forest regressor with a value of 0.91. That's about 0.09 values away from 1. So we can determine, as I said, for root mean squared error, the closer it gets to 0, the better the model is. For r squared error, the closer it gets to the closer it gets to 1, the better the model is. So we can tell that random forest regressor, both in root mean squared error and both in r squared, is the best because it tends to get to 0, is the closest to 0, and is also the closest to 1. So now I decided to try using k-fold cross validation just in case, maybe to try another method, see if I will get the same thing or if it can be evaluated better. Remember, the goal for the root mean squared error is to get it closer to 0, and the goal for the r squared error is to get it closer to 1. So here are the values when the models were evaluated using k-fold cross validation. So each row is a fold. The first fold, the second fold, the third fold, the fourth fold, and the fifth fold. Each row is a fold. Now we can see that k neighbors regressor is still there again with the highest values. We can see it's having 37, 36, 37, 36, and 40. But then we have our random forest regressor. Okay, in the first fold, where we have 19.358519, we can see that random forest is the highest with about this is the root mean squared error, by the way. So remember, we need the closest to 0. We have random k neighbors regressor with a value of 37.76487 there, and then we have random forest with a value of 14.135804. So in that first fold, random forest regressor performs best. In the second fold, we also have the same thing with k neighbors having a value of 39.679 and random forest having a value of 13.359. That is even lower than the decision. That's even lower than the random forest for the train test split. Now we have the same thing in for 3, 37.12. We have 14.99 in 4 in as for random forest. By the time we finish looking at all these values, we can tell that each and every time in every fold, random forest regressor always has the value that is closest to 0, which makes it the best model out of all these models to perform or to predict the values for the testing set. So now we've been able to determine that random forest regressor is the best used for predicting the values of the equation of PM 2.5. So using that said model, the values are then predicted. Let's take a look at the results. Now we can see a column for the predicted values and a column for the true values, right? So the one that has 0, we have the 0 row. We can see that the predicted value was 123 and the true value was 132. We can see that the predicted value was 86 and the true value was 93. Now coming down, we can see that in 8,996, you can see that there's just a difference of 3 between the predicted value and the true value. Even in 895, we see that there's just a difference of about 2 in the predicted value and the true value. So we've been able to, since we were able to determine the model that will best be used, which we determined was random forest regressor, to predict the values, we were able to get our values, and these are our results. Now for the classification task, again we had to determine what model was best to be used to classify these already predicted values. So now we have our values, we have the predictions, we need to be able to classify them into low and high. So we use logistic regression. The models that we are tested: logistic regression, k-neighbors classifier, decision tree classifier, and random forest classifier. So using the predicted values, like I said earlier, the concentration would then be sorted into high and low. To determine the best model to do that: false negatives, true negatives, false positive, true positive, true positive rate. I'm sorry, that's supposed to be true positive rate, and false positive rate scores will all be calculated. Then an ROC curve is plotted. Now remember, for an ROC curve, as the value tends to 1, the model that tends to 1, when I say quicker or at an earlier time, is the best model to be used. Now let's take a look at this ROC graph. We can see that the logistic regression, the blue line, which is the blue line, it's tending to 1, as all of them will eventually converge at 1 at a particular point. In this case it's 1, but it tends to 1, and we can see that it tends to 1 around the greater than 0.9 mark. We can see it tends to 1 around 0.9. We can see that's when it finally reaches that 1 line. Now we take a look at the KNN, the KNN classifier, and we see it tends to 1, and again it reaches 1 around greater than 0.9 mark. Now we have decision tree, we also tends to 1, which also reaches 1 around that 0.9 mark. But here we have our random forest. Starting or reaching 1, it reaches 1 at around the 0.5 mark. So then again, random forest classifier is now determined to be the best model to use to classify the data values, because as it tends to 1, and out of all the models, it reaches 1 the quickest. You will see it reach 1 at 0.5. So that's why it's determined to be the best model to use for classification. So just to briefly go through this, from the curve, it is determined that random forest classifier is the best for classifying the predicted values of the equation of PM 2.5. As they all approach 1, the random forest classifier is closer to 1 and even reaches the 1 mark at greater than 0.4, while other models reach the 1 mark at greater than 0.9. In conclusion, these results show the ability of machine learning algorithms in predicting ambient PM 2.5 levels. More so, it shows the effectiveness of the random forest regressor and random forest classifier in predicting and classifying the levels of fine particulate matter in the environment, and in urban cities in general. It has proven to be not very accurate, but random forest classifier and random forest regressor has proven to be the best out of all the other models in predicting and classifying the levels of fine particulate matter. Thank you so much for watching my video. Thank you so much for watching and learning, for being here and learning more about my project. I hope you have a lovely day. Thank you. Bye.